So thanks for having me here. I'll be talking today about bipartite experiments and applications to marketplace experiments. This is joint work with Fredrik, David, Vahab, and Jean. So before I give any talk, I just like to tell the audience I'm a person who stutters. I get more comfortable when I say that. I hope you get more comfortable hearing it because you're going to hear it for the rest of the talk. Okay. So in randomized experiments, we typically consider settings where we treat and measure outcomes on the same unit. So suppose you're going to test some drug and how effective it is compared to a placebo, and you have these participants come in. I've drawn them here. You give some of them the treatment and some of them the control. And after that, you sort of measure what their outcomes are. Maybe it's a health outcome as I've drawn it here. But the important part is that you typically assign treatment and measure outcomes on this one patient, or these N patients that you have. And so the question is, how should we think about experiments where units which receive treatment are distinct from those units on which we measure outcomes? So I may try to treat some auction by changing some reserve price, and I want to measure what that changes on the bidder behavior. Okay, so one framework in which to do this is the bipartite experimental setting. It's introduced by Ziegler and Pouget-Abadie, and treatments are distinct from outcome units here. So one example, and the one that motivated them, is this public health example here, where they have power plants on the left and hospitals on the right. And they're trying to investigate the effect of air pollution from power plants on the nearby hospitals. And so I've drawn edges here where there exists an edge if the power plant is within a certain range of the hospital. And so what we're going to do is we're going to assign treatment to the power plants. Maybe it's one of several pollution reduction plans, and we're going to measure outcomes at the hospital level. So maybe the number of patients with a certain lung disease. And the analysis in this paper here assumes very little about the way in which treatment on power plants could affect outcomes on the hospitals. And so because they assume very little in that respect, they have to assume the bipartite graph is essentially the union of small disconnected components. And that assumption may be fine in some cases and not so fine in others. So suppose that you're in a marketplace setting. We are eBay here. And we're going to consider the effect of different auction formats on bidder behaviors. So we have this real online marketplace here. There are some items that we're going to be bidding on, pots and pans and pants. And we have bidders who were on my dissertation committee. And now I'm going to put lines and make a bipartite graph if that bidder participates in that auction. And so we're going to investigate the effect of auction formats, maybe changing a reserve price, on bidder behavior. Maybe it's their spend or their engagement measured in some kind of way. So we apply treatment to the auctions. We measure outcomes at the bidder level. And here's the thing. We know that complex interactions exist in the sense that this bipartite graph won't be the small union of disconnected components, because it doesn't come from some kind of spatial setting like it did in the last time. Instead, we know these complex interactions are going to exist, and in this setting, inference is only possible under structural assumptions about the relationship between the treatment at the auction level and the outcomes at the bidder level. And so that's what we're going to be exploring in this paper here. And the question is, how can we leverage structural assumptions on the outcomes to construct point estimates and valid inference in the bipartite setting? And something that's in the paper but I won't discuss here is how can we construct designs, that is, the random assignment of treatment, which appropriately account for this bipartite structure. So in this talk, we present a linear exposure response assumption for bipartite experiments, a new point estimator, which we call the exposure reweighted linear or EARL estimator for estimating the all or nothing treatment effect, and we'll show it has nice properties. And we're going to have an unbiased variance estimator, which will allow us to get confidence intervals. And in the paper, we do some experiments, and we also suggest a correlation clustering-based design for improving the precision of the point estimator. And there's a lot of related work in randomized experiments. They typically assume there's no interference between the units. That is, my treatment does not affect your outcome. That's the Sudfa assumption. So there's a long work in interference in experiments that started maybe in 2013. I've only listed a few things here. And the bipartite case has been a special case in the recent years. And I also want to mention there's a lot of work in two-sided marketplace and experimentation, especially some interesting applied work and some work from the OR community that I'd like to talk about at the very end. OK, so let's get into the setting, what the model is. There are M treatment units. These are the power plants. We have N outcome units. These are the hospitals. And I'm going to denote them by integers j and I. I might get those mixed up, but hopefully it should be clear from the context. Each treatment unit is assigned one of two treatments. These are like the pollution reduction plans. And they're denoted Zi. They take values in 0, 1. And we're going to collect those treatments into a vector. It's of length m, because there are m treatment units, and it has entries in 0, 1. And the experimental design, or simply the design for short, is the distribution of random treatment assignment vectors. And in particular, this design is chosen by the experimenter, so it's known. And treatment assignment is the only source of randomness in the potential outcomes framework that I'm working with here. So I'll discuss that a little bit more later on, but I want to emphasize that this is the only random thing that will be going on. OK, so let's talk about the linear exposure and what the outcome functions are. So every outcome unit has a potential outcome function. We'll call it yi, and it maps the treatment assignment vector, how all of the power plants received their treatment, to the reals. And this is mapping treatments to outcomes here. That's what yi is. And the exposure of an outcome unit is a linear combination of treatment assignments. So this is, for some outcome unit I, its exposure it receives is some function of the treatment assignment vector, namely this known linear function here. So we know what these weights are. And I'm going to assume in this talk that they're normalized, they're non-negative, and they sum to 1. And so we can interpret these known coefficients as being weighted edges in a bipartite graph. So we have the outcome units on one side. We have the treatment units on the other. We assign treatment to the treatment. Oops, this is the weights. We assign treatment to the treatment units here. And they become exposures on the outcome unit side. And what we observe is the outcome function evaluated for that treatment assignment and what the exposure is. And so what's left now is structural assumptions on the outcome functions. How do they look? And we assume that they are linear in the exposures. So each unit I, the outcome that it has is some beta I times its exposure plus some intercept term alpha I. And I want to emphasize that the response yi of xi is what's observed. These parameters, beta I and alpha I, they are unobserved. And we run the experiment once, so we only have one value, one evaluation of y, so we can't hope to learn these parameters here, at least not in any reasonable way. So the con of an assumption like this is that the linearity of the response is kind of a strong assumption. I'm not allowing for any kind of diminishing returns, although we can, in follow-up papers, we can handle stuff kind of like this. The pro, though, is that we maintain heterogeneity amongst the units here. So every unit has its own specific outcome function. There's nothing tying them together necessarily. And this type of assumption, some kind of linear assumption like this in some exposure, is one that's common in the interference literature. Not exactly as we've stated it here, but this type of idea has come up before. And in this paper, we're interested in estimating what we call the average total treatment effect. And this is the average over all units of two outcomes. The outcome where everyone received treatment minus the outcome where nobody received treatment. So how many people come in sick to your hospital if every power plant gets this reduction scheme versus how many people come into your hospital sick if we do the control plan. And under the linear response assumption, this is simply the average of the individual slope terms. And at this point, I would like to emphasize again that we're working in a finite population design-based inference framework. And what that means is there's no data generating process that I've assumed about these units or the outcomes that they have. These are all deterministic things. And the only randomness and the basis of all of my inference is the randomization of treatment assignment. So I just want to emphasize that. Before I move on, are there any clarifying questions about the model here? Yes?
How is this clarifying? So you decide if it's not.
Okay.
Ask it later.
Mm-hmm.
So are you allowed to experiment in 2 shots instead of 1? Because of the particular objective you have, one simple experiment that comes to my mind is first give treatment to no one, then give it to everyone, and then subtract the outcomes from each other. That would be.
Yeah, so we're not allowing, so the question was, can you run 2 experiments? No, you can only run 1. And maybe we can talk a little bit more about it offline, but I think that this body of work, especially people who do epidemiology and stuff, they might say, well, you're going to run a different experiment later. So what, in 2 years maybe? Well, now these are different people. It's not even the same person. So it's kind of like a snapshot in time, if you will. That's kind of how we like to think about it. Great, thanks. OK, so how should we estimate this quantity here? So here's an idea. For each slope term beta I, let's construct an unbiased, but maybe it has a high variance estimator tau hat I. And we're going to average them to obtain an estimator for the average total treatment effect. And if these individual estimators, they may have too high variance to be worth anything, but once I average them, if they have small enough correlations, they should get a pretty good estimate of the average total treatment effect. And that's kind of what we're going to do here. So we propose the exposure reweighted linear estimator. We call it the Earl estimator here. It's very simple. What you do is you average the outcomes that you observe times some normalization factor. And that normalization factor depends on the observed exposure and the 2 statistics of the exposure distribution. So we take the exposure, subtract off its mean, divide by its variance. And that's what our estimator is. It's a very simple one. And so we show the estimator satisfies the following guarantees. First, that it's unbiased. This holds in finite samples, and it kind of works the way that I said last time, that each individual term here gets that slope. And this is true only if the variance of each exposure is non-zero. That is, you have to have 2 different exposures you could possibly see. And for a wide class of designs, these cluster-based designs, we show that this estimator is consistent in mean square error if the outcomes are bounded, they can't grow large, and the graph has to be sufficiently sparse. If everyone's connected to everyone, then everyone's outcome depends on everyone's, and you can't handle that. So we have some conditions there in the paper. And we have a similar guarantee for asymptotic normality of the estimator as well, but the conditions on the growth of the bipartite graph, those are a bit stronger to obtain the central limit theorem. And something you might ask is, OK, if this linear exposure response assumption doesn't hold, what is the Earl estimator estimating? So I showed it was unbiased if the linear exposure response assumption holds, but what is it doing if that is not true? So we have this theorem that the expectation of the Earl estimator is equal to some average treatment effect, not on your outcomes, but on outcome functions y tilde, where these y tildes, they are always going to be linear functions, and they are the best fit to your true unknown functions. And by best fit, I mean with respect to the design, with respect to the sampling that you actually do. And so some way to interpret this is that even if you don't believe the linear exposure response assumption, the thing you're estimating is the average total treatment effect on the best linear fit of the outcomes to the exposures. And maybe this is still a policy relevant quantity, and it's close to the average treatment effect, even if linearity almost holds. OK, so those are some of the results. Now, motivated by the normal limiting distribution, we can construct normal-based confidence intervals in the usual way, or we would like to. The problem is that we need to know the variance of our estimator. And this is something that if we run the experiment once, we can't know it. It depends on all of the outcomes. So we have to estimate it. And this is called a variance estimator. And we derive one which is unbiased under mild conditions on the exposures. And it's a new method of variance estimation that really relies on kind of the fact this exposure is kind of a continuous and not a binary thing. And this is kind of surprising because unbiased variance estimation in design-based frameworks are typically not possible. You have to have a conservative estimate. So it's kind of surprising we can do that here. And this gives us asymptotically valid confidence intervals. And how much time do I have left, by the way?
2 minutes.
2 minutes. That's perfect. So just to conclude, I have 2 last slides. We investigated the linear exposure response assumption and proposed a new method of point estimation and inference. There's more results in the paper. We have simulations that we run. Not all designs are created equal here. You shouldn't independently do treatment assignments, but you should involve the bipartite graph. So we have a cluster-based design that works well. There's a couple open problems, some technical ones in the statistical inference side. First, like how do you handle interference between outcome units? So we really kind of put all the interference in the bipartite graph, and it really depended on the treatment units. How do you have interference between outcome units? How can you have more principled designs? The one we have is kind of a heuristic, and we'd like to have designs under which we can prove better or weaker conditions for consistency and normality. And I talked about it a little bit, but we'd like to have better sensitivity type of results. If your model, the linear exposure response assumption, is wrong, how wrong are your estimates? In particular, those confidence intervals is what's very hard. And there's some work out there that addresses something like that, but I think it's still very much an open question. I'd like to end on one more open problem here, which is kind of 2 communities that are looking at these marketplace experiments. I think they both have pros and cons, and I'd love to bring them together in some way. So this work is in the causal inference world, the randomized experiments world. And what we're good at doing is design-based methods for valid statistical estimation with high levels of heterogeneity. The cons that our community has is that the interference structures that we posit right now may not sufficiently capture the marketplace setting, may not look, very much like a marketplace. Okay, there's a modeling approach that I see coming out of the OR community that I like a lot. And they have lots of pros. They have very rich and complex realistic marketplace models, albeit they have some heterogeneity like unit types. What they're very good at is identifying market conditions where the naive estimation, the one that doesn't take interference into account, where those fail. Maybe it's the ratio of supply and demand, and that affects the bias. And there's wonderful results that kind of characterize this under these models. And the cons is there's not as good or as precise methods for how to fix the bias in the point estimates or to fix the non-validity of your confidence intervals. And I would love to combine the best of these both worlds, and I think it's something that both people would have to come together to do here. That's all I have. Thanks for letting me talk here, and I'd love to take any questions that you have.
All right, I have a question. So I'm curious if you believe that linear treatment effects aren't appropriate. Presumably both bias and variance break if you think about generalized linear models of that treatment effect. Is that right?
Can you say what you mean by generalized linear models?
I mean...
and then I'll repeat the question, but then
although
yeah.
I did ask it into
the
mic.
The mic. So. Yes, no, I don't have to repeat anything then.
Okay.
Great.
So all I mean is that, okay, so if we assume that my outcome is just a function of some stuff which is linear in my neighbors, right? I could imagine thinking about it being linear in quadratics of my neighbors.
Yes.
Yeah.
Yes.
Does everything break?
Everything that I just put on the screen breaks, but we have a forthcoming paper, which I'll write down to send it to you if you're interested. I guess, yeah, right, you already said what the question was. Yes, we can handle interference structures like that. So we have this new paper, Fredrik and I have this new paper with Yitan, where we look at exactly interference classes like this and how to derive estimators. And a lot of those techniques come from this technique here. It's a very similar type of idea. Well, it's not obvious, but it's all, if you look at the sauce long enough, it's there, yeah. But misspecification is still very hard. Like you have to assume that your model is correct. Yeah.
Any other questions?
I think I see one in the back.
Yeah, based on, could you just, if it's not too technical, comment a bit on what sufficiently sparse would be here? Is it like little events, square edges, or
Yes, there is. So, Oh, repeat the question. The question was, what does sufficiently sparse mean? Could you be more technical on that? And the answer is yes, I can be. But the answer to your question is it goes essentially like this. Define for an outcome unit, it's like second order neighbors as all of those other outcome units that share a treatment unit they are connected to. Call that the neighborhood. For consistency, you want the average neighborhood size to be constant. And for normality, you want the maximum neighborhood size to be constant. And so some way you can get this is if you put like conditions on that the degree of both sides are not too large. The degree of one side or the other side are not too large. That's what it looks like. Yeah. Great, well, thank you.